Thank you very much. First of all, I would like to thank the organizers for the kind invitation. Maybe I should apologize with the audience for proposing a talk which is not completely within the topics of the conference. I'm not talking about the fluid flows, but about chemotaxis. Anyway, this is a joint work with Piotr Bieler from the University of Wrocław and Alexandre Borichev, a colleague of mine in Lyon. And so the topic is the Keller-Segel system for chemotaxis, and the main issues will be the global existence of solutions or their finite time blow-up. So this is the system that we are going to consider. It is the Keller-Segel system in its the simplest formulation. We assume that we have a population of microorganisms, they can bacteria or cells, that they can move, and they are also able to emit a chemoattractant, phi, and this chemical signal helps the population to organize itself. And there is a competition between the natural diffusion. So the unknowns are the density of the population and the density of the chemoattractant. And there is a competition between the natural diffusion given by the Laplacian that tends to spread out the population, and this forcing term, which is proportional to the gradient of the concentration that tends to approach the population of the cells each other. And the second equation is just a parabolic equation for the evolution of phi. Here the parameter tau is usually very small in the biological application because the diffusion of the chemical is faster than the diffusion of the population of cells. And there is one interesting limit situation in which you take the limit as tau goes to 0, in which the second parabolic equation boils down to an elliptic equation. So you get, in this case, the parabolic elliptic Keller-Segel system that plays also a role in astrophysics as a model for the dynamics of self-gravitating particles in nebulae. So a very important feature of Keller-Segel is the possibility of having solutions that blow up in finite time. And the blow-up feature, the blow-up properties is especially well understood for the parabolic elliptic system, especially in the case of the dimension 2. So in this case, we have a threshold phenomenon. So if the total mass of the population is above 8 pi, then a solution will blow up in finite time. And the first work in this direction were by Jaeger and Luckhaus a long time ago, assuming that the second moment were finite. And on the other hand, when the total mass is below 8 pi, solutions are proved to exist globally under general assumption, and the limit case 8 pi was settled by Blanchet, Lorenzo, and Parker. So this for the dimension 2. When the dimension is larger, still we have a blow-up criteria. And for example, this criterion that you have to compare the moment of U0 with the total mass. And if this is small with respect to a power of the total mass, you have blow-up in finite time. And the interpretation is that you are assuming here that you have a good concentration of the population at the beginning. Okay, for the parabolic-parabolic system, the blow-up problem remained open for a long time. And in fact, the only available result was made recently by Winkler, who proved the blow-up. But to some extent, the situation is still quite open because Winkler results is available only for radial solutions. So nothing is known for non-radial solutions. Okay, this for the blow-up. Now for the global existence, the very basic observation is that you have some scaling invariance for Keller-Segel, so you can start to obtain the global existence just assuming that in some scaling invariant space, the initial data is small. Very often in the literature, one assumes that the initial concentration is 0. This is not essential for the mathematical analysis, but it simplifies the presentation, and I will often assume that phi 0 is equal to 0. So, for example, assuming that U0 is small in such spaces in L d over 2, you get easily global existence. But you can do better and use a larger space. For example, you can assume that U0 is small in the pseudo-measure space, or in the case d equal to using finite measures instead of L1. But you can also use a weak Lebesgue space, so it's done by Cosone and Sugiyama, or Sobolev space. And Iwabuchi studied the global existence using Bezos space. And one motivation of considering a large space, raw space, is that you want to encompass inside the theory some particular solutions, and the best known in dimension 3 or larger is the Chandrasekhar solution, which is a steady state of the parabolic elliptic system, and that plays a role in the theory of black holes. Okay, now what is all these space have the same scaling. What is the largest space? It is well known that all previous spaces are embedded in such a Bezos space, which is the largest factor space, which is both invariant on the translation and under the scaling of the equation of Keller-Segel. And a nice remark of Pierre-Gilles Lemarrier is that when one assumes that U0 is larger or equal than 0, which is of course the physical assumption for Keller-Segel, then it is equivalent to ask that U0 belongs to such a largest Bezos space, or to assume that U0 is in the Mori space md/2. Here I'm with norm equivalence. Here I'm recalling the Mori norm, so space of locally finite measures, such that the measure on a ball is bounded by some power of the radius, and the power is chosen in such a way that this Mori norm rescales like the usual LQ norm. So the result of Pierre-Gilles Lemarrier I was mentioning is the following. It simply states that if the dimension is larger or equal than 2, the parameter is larger or equal than 0, so it applies both to parabolic-parabolic and parabolic-elliptic Keller-Segel. Then you can get the global existence when you assume that you have an initial data U0, which is small in this Mori md/2 space. And the global solution is constructed in a space of Mori time, so in a space of function that depends on x and t, such that for all time they belong to a non-classical Mori space, because here we need to use a Mori space which is modeled not on the classical Lebesgue spaces, but on weak Lebesgue space. So it is a more technical Mori-Marcinkiewicz space. So what I would like to stress here is that the size condition is uniform with respect to the parameter tau. And this is both good news and a bad news. So it is a good news because having here something which is uniform in tau paves the way in establishing convergence results of solutions of the parabolic-parabolic system towards solution of the parabolic-elliptic system when tau goes to 0, which is an important problem in chemotaxis. There were results by Rajinsky some time ago, but the functional setting was much more restricted. So here it is possible to prove, in fact it is done in the paper by Lemarrier, it is possible to prove this convergence in a much wider setting using the EB norm. Now, the bad news is that when the parameter tau is large, one would expect that it should be possible to prove the global existence relaxing the size condition. So this is the question that you raised. What happens when tau is large? So I review here a couple of papers in this direction that address the problem of the global solvability for large value of the parameter tau. So here in the first line, I'm just recalling Lemarrier result. We have a size condition uniform in tau. In the case of the dimension 2, Correas, Escobedo, and Matos relaxed the size condition and got the global existence assuming that the size can be up to tau to the power 1/2 minus epsilon. And a similar result was established also by Bieler, Guerra, and Karch, but in a slightly more general sense. So these results were in dimension 2. So the starting point of our analysis was to extend these results to any dimension. And a byproduct of what we did is that we could also drop the epsilon here. And so we got the global existence assuming initial data of size the square root of tau. So this is how we did. First of all, as many others, we assume for simplicity that phi 0 is equal to 0. And we start dropping the unknown phi. This can be done easily because you can express the gradient of phi in terms of u introducing this linear operator. Next, you use this linear operator to introduce this bilinear operator b of uv, and in such a way that you can recast the integral form of Keller-Segel, or parabolic-parabolic Keller-Segel, in this way, which is familiar to all of you, where u0 is just the solution of the heat. So what in the two papers that I mentioned before, the authors solved this by making a fixed point in a subspace of functions that are continuous in time with values in a set of finite measures, or in L1. But in order to extend to arbitrary dimension and also to remove the epsilon, we make a slightly different choice. So we rather work in the space of functions that are just locally infinite in time and the values in LP with the suitable decay for the LP norma that guarantees the scaling variation of this space. So when we work with this, we naturally have to introduce Bezos spaces because it's a classical fact that the caloric extension of U0 belongs to such space EP if and only if U0 is in a Bezos space with the norm equivalence. And so the only thing that you have to do is to establish the relevant bilinear estimates in the space EP. And there are some, this is the estimate that can be proved without particular technical difficulties. The only point that I would like to stress is that contrary to the Lemaitre functional setting, here the bilinear estimates explicitly depends on the parameter tau. And then P and Q have to belong to appropriate ranges, but for example, if you're interested in the case when tau is equal to 0, the best choice is to take the Q as small as possible, so in fact Q equal to P. The bilinear normal behaves like 1 over the square root of tau, which gives you an existence result when the base of norm is of order of the square root of tau, with some restriction on the parameter P. So here, in this kind of result, you don't even need to assume that U0 is non-negative, but of course you should add if you want to give the biological interpretation of this. So this theorem motivates the following question. Is the square root of tau the largest possible size condition that one is allowed to put if one hopes to obtain a general global existence result? We wanted to, first of all, to have a guess of what the correct answer should be. And so to have such a guess, we decided to introduce a couple of toy models. I will spend some time for introducing such toy models. Both toy models are obtained replacing this nonlinear term of the parabolic-parabolic Keller-Segel with another nonlinearity, which is the same scaling and the same order. So in the first toy model, we use the product U Laplacian of phi, and in the second toy model, the Laplacian of phi squared. A serious objection is that if you take Keller-Segel and you remove this drift term, you are putting away one of the essential features of the system. So I would not suggest to use the toy models for any prediction about chemotherapy. But for the mathematical analysis, it is okay. So the first toy model, as I mentioned in the first equation, you have a ut equal to Laplacian of u minus u Laplacian of phi. In the second, you have Laplacian of phi squared. We do not modify the second equation, which is exactly the same that we had for the usual parabolic-parabolic. Okay, so let me observe that both models, in the limit case when tau is equal to 0, degenerate into a nonlinear heat equation with a quadratic nonlinearity. For the same, simply because in the limit case, the Laplacian of u, the Laplacian of phi is equal to minus u. And for the same reason, also the steady states of these toy models are the same as the steady states of the quadratic heat equation under a compatibility condition of phi. So concerning the existence part, we can proceed more or less as we did for Keller-Segel. I will just give some overview in the case of the first toy model Tm. So we treat this as a perturbation of the parabolic-parabolic, writing u Laplacian phi as the usual drift term minus gradient of u gradient phi. And so we get two bilinear operators we have to study. And the first one is just what we did before for Keller-Segel. Here we need some additional information on the gradient of the solution. So instead of working in the space EP that I had before, we take a smaller space in which we get, we want to have some additional information. So we ask to u of t to belongs to the Sobolev space and to have some the appropriate decay condition for the gradient at the time t in the LP norm in order to respect the scale. So using the bilinear estimates in this space, you get a statement which is similar to the previous one, global existence under this size condition for the base of norm, and uniqueness in a ball of the space Fp. When you give a closer look, since you need to do more estimates here, you need more restriction on the parameters. At the end, you find that this is not compatible when the dimension is 2. And so this result holds for the dimension 3 or more. Probably a different functional setting would be needed to handle the case of the dimension. Okay, now the main motivation for this toy model is that the blow-up analysis can be quantified in a more precise way than for the usual Keller-Segel. So this is the blow-up result for Tm, which is deeply inspired by a similar blow-up result given by Montgomery-Smith for the cheap Navier-Stokes equation, which was a toy model for Navier-Stokes. And the theorem states the following. Assume that tau is larger or equal than 1, just for simplifying a little bit the statement, but tau larger than 0, it is also okay. Assume that phi 0 is equal to 0. We start with u0 in a Schwarz class. And we assume that the Fourier transform is bounded from below by the constant times the indicator function of the ball. Then, provide that the size of A is large enough, larger than a constant multiplied by tau, then the solution of Tm blows up in finite time. And everything is done using elementary Fourier transforms. So we start writing the relation between phi and u using the Fourier transform. We have to handle the nonlinearity, which is a u Laplacian of phi for the first toy model. So in the Fourier space, this gives such convolution type integral. And then the integral equation that we are going to study is this one, which is obtained simply when you replace this identity inside the second equation. So we are going to study this integral equation. And the important feature is that if the Fourier transform of u0 is larger than the Fourier transform of another initial data w0, which is positive, then this will be conserved by the flow of Tm. And so the corresponding solution arising from u0 will have a larger Fourier transform than the solution arising from w0. And so we can reproduce this remark many times. In fact, using some inductive procedure. So in the first step, we choose the appropriate w0, and we just we look for lower bound estimates for the Fourier transform. So we just bound from below u hat, just retaining the linear part of the equation. In the second step of our iteration method, we bound from below retaining the linear part plus some contribution of this integral, in which in the second step we instead of u hat we replace the linear part of the equation, and then we continue in this way. So what is a good choice for W0? We just take the indicator function of the ball, but it is better to take a ball which is not centered at the origin, because you get a better lower bound estimates for the integral term that we had before if you take a ball which is slightly away from the origin. So we take a ball which is centered around the point 1, 0, 0. And then we proceed by induction. We define wk hat as the convolution of wk minus 1 hat with itself, which is supported in a dyadic ball, which is supported in a dyadic annulus. And in this annulus, we can perform the lower bounds of our integral. And so the technical lower bounds are summarized by the following lemma, which is the essential step of the proof. So if u0, okay, by contradiction, we are assuming that we have a solution that it is defined at least in a time interval 0, 1. And then in this case, if the Fourier transform is bound from below by w0 hat, then for all integral k, we can bound from below our solution in the time interval where the solution is defined by the function wk hat that I introduced before by induction. There is a time-dependent coefficient here, but in fact it turns out that when the time is large enough, in fact at the time t equal to 1, all these lower bounds will hold. We have here in front a bad term, because this decay is very fast when k goes to plus infinity, so for the lower bounds this is not good, but you can play with the size of the initial data, and if you take a size which is larger than a constant multiplied by tau, you can get a beta chi sequence which is very fast growing, like a double exponential, and you can kill the fast decaying term, and at the end this argument gives you a blow up at the time t equal to 1. So now, summarizing, so far we have global existence for parabolic-parabolic Keller-Segel, or for the two toy models for size for initial data with size square root of tau in some norm, and you have a possible blow up for size condition of order of tau. So still we have a huge gap here. And so how to reduce this gap? Bezos space seem not to work, because at best we get this. If we take a larger space, it seems to be even worse, because as in Le Marier result, we just get 1 here. So let us try a smaller space. Not too small, because still we want to include some similar solution inside this analysis. And on the other hand, since the blow up here was obtained with the Fourier transform, let us try to get a global existence result just using Fourier transform, hoping that the estimates are sharp. So these considerations lead us to work in a pseudo-measure space. So a pseudo-measure is just a temporal distribution with L infinity Fourier transform. But this notion was generalized, introducing the space PMA of tempered distribution, such that the Fourier transform is bounded by a constant divided by xi to the power a. And of relevance for the Keller-Segel is especially the case a equal d minus 2, because we get the invariant space with respect to the scale. And pseudo-measures were also already used before for Keller-Segel by Bieler, Canone, Guerra, and Karch. But in the case of the parabolic elliptic system, constructed solutions in the space of functions that are L infinity in time with values in the invariant space P, M, d minus 2. Okay? For later use, I will call eggs this. So we did a slightly different we choose a slightly different functional setting, but still of pseudo-measure types. So we make our fixed point in YA, which is the functions which are infinitely local in time with values which are in values, in fact, in the pseudo-measure space PMA. Okay? And so this is the theorem. It is the only slide in which I allow phi 0 to be possibly different than 0. So assume that we are in dimension d larger than 3, tau is positive, u0 is in the invariant pseudo-measure space. We can guarantee the global existence of solutions under one of the two following size conditions. So in the first size condition, is interesting when the parameter tau is small. Let us notice that here we have the square root of tau in front of phi 0, so which means that when tau goes to 0, you can take an initial concentration which is large enough. And the second size condition is interesting when the parameter tau is larger than 1. So basically, here you have an arbitrary parameter b strictly positive. And so the size condition for u0 is like tau to the power 1 minus. And the global existence works for the usual Keller-Segel of the two-tone model. The solutions are constructed in a suitable in the space YA for a suitable choice of A, where the parameter A depends on tau, depends on the dimension, and depends also on the choice of this parameter B. After constructing the solution in YA in a ball of the space, the solutions turn out to be also in the space eggs that I introduced in the previous slide. Okay? So a couple of remarks on this statement. So I mentioned that the theorem was for the dimension larger or equal than 3, but at least for the parabolic-parabolic, we can handle also the case of the dimension 2, but we have to strengthen a little bit the size condition when tau goes to 0. So this size condition for the case of the dimension 2 is more restrictive than the previous one. And the second observation is that here the parameter b in 0, 1 is arbitrary, and you can tune depending on what you want to achieve. For example, if tau is very large and you're interested in getting the largest possible size condition, then you should choose b equal to 3 divided by the logarithm of tau, so a parameter which depends on tau. So we get in this way the following corollary, in which I assume back that phi 0 is equal to 0. So in dimension larger than 3 or larger or equal than 3, when u0 is an invariant pseudo-measure space, provided that the pseudo-measure norm of u0 is less than tau divided by the logarithm of tau cubed, then we can get the global existence. The solution will belong to such space yd minus 4 divided by logarithm of tau, unique in a ball. We do not expect uniqueness outside the ball because, in fact, there are non-uniqueness result in dimension for such similar solution. And this works also for dimension 2 in the parabolic-parabolic